I share the screen here so that we can see this. And I want to hide names of annotators. Okay, like I was saying, there were some interesting choices of tests to apply. The first one, of course, diverges. Okay, why? Well, I mean, you could apply like the p-series test or something if you wanted to, yes, because it's basically like, you realize it's basically like the harmonic series, yes, essentially multiplied by 4/7. The second one converges, and I think probably the easiest thing to apply is the root test. If you use the root test, the nth root of 5, that goes to 1. The nth root of n to the 7, that goes to 1. The nth root of 6 to the n goes to 6. So overall, the nth root of that entire thing will go to 1/6, which is smaller than 1, so you get convergence, yeah? The letter C, pretty clearly that one's going to require the ratio test. Now, some of you, I was very gentle, some of you tried to do things like direct comparison, and I wasn't sure how you were doing it, but some of you actually wrote some stuff to show why direct comparison would work. Letter D diverges, and that's basically just nth term. I mean, think about it. The terms themselves go to a third. That's bad, right? Some of you use things like limit comparison, and I suppose you could do that, okay? Letter E converged, and that there's a couple of options. I mean, you could use direct comparison with a p-series if you really wanted to, okay? But you could also use the integral test, and some of you even said logarithmic p-series, which I accepted. So there's any number of options here, okay? So I wasn't super picky about that, okay? This next guy right here, or these next two guys, they both converge. And this guy's a geometric series, and it's basically going to be the first term, which is 5 times -7/9 to the third, all over 1 minus the ratio, which is -7/9. And I mean, you would have to simplify that a little bit. Some of you didn't realize that, the first term here was not to the 0 power, okay, which is something you had to recognize. Okay, the third one, if you kind of write out the first few terms, you start to realize what's going on here. Or the second one, letter B, you start to realize what's going on here. If you plug in n equal to 2, you get 3/4 minus what? So 2 plus 3 is 5, minus 3/25. Okay, and then it's plus 3/9 minus 3/36 plus 3/16 minus 3/49 or something like that, right? And then we start getting some stuff that that is repeating. So the next one is going to be 3/25 minus 3/64 plus etc. So at this point, you kind of realize what's happening. The 3/25, well, that's going to cancel with this guy. The minus 3/36 is going to cancel with something up here. The minus 3/49 is going to cancel with something up here. The minus 3/64 is going to cancel with something up here. So what's the only thing that's going to be left in the end? Well, 3/4, and then 3/9, and then 3/16. Okay. I mean, you could have written down what the nth partial sum is to kind of sort out what that is precisely, and then take the limit as n goes to infinity. But it's essentially those first 3 positive terms that end up surviving. Everything else cancels. Okay. I was very kind by not giving you something that you had to, although some of you still tried to use, partial fraction decomposition, even though I already did it. Yeah? Some of you still did it and then ended up with the same thing right back. You're okay, and you were like, wow, something's not right. That's okay. Sometimes that's just what happens. Okay? Okay? But I was very kind by not making you do that. Okay, this guy right here, basically if you use, basically if you use limit comparison, essentially this guy is going to behave exactly like, the harmonic series. And therefore, what's going on with this? Yeah, diverges, right? So this is basically limit comparison test, if you will. This guy right here, if you apply the root test, and you take the nth root of this beast, 1 over 3 plus 5 logarithm of n, all raised to the 7n, you end up getting 1 over 3 plus 5 logarithm of n raised to the 7th, which clearly goes to 0 as n goes to infinity, which is less than 1. Therefore, this thing does what? Converges by root test. Okay, now, some of you did some clever things like a direct comparison by dropping the 5 logarithm of n, for instance. That would work, okay? But probably the easiest thing to do is the root test on this one. Any questions on that? Okay, next. All right, these ones, I said that you needed to say, if you had convergence, whether that convergence was absolute or conditional. Now, some of you are real sloppy with your minus signs, and you're paying a huge price, and I was pretty gentle about that. But some of you tried to use the alternating series test on A. That's unnecessary. If you just take the absolute value of this thing, the minus sign goes away, and the thing is going to converge even in absolute value, which means it's absolutely convergent. If you take the nth root of the absolute value of this thing, okay, negative 4n over 7n minus 1 to the n, then what you end up with is the nth root goes away, the minus sign goes away, and you end up with 4n over 7n minus 1. And as n goes to infinity, what does that go to? Well, 4/7, which is less than 1. Therefore, what's the conclusion? This thing converges how? Absolutely by the root test. Okay? Any questions on that one? So that thing converges absolutely by the root test. Okay? And some of you are getting sort of sloppy with your cancellation of things. But if you take the absolute value of an plus 1 over an, in this case, first of all, the minus sign just becomes irrelevant, yeah? And what you're going to end up with is n plus 1, 7 to the n plus 1 over n plus 1, which is n plus 2 factorial, divided by n 7 to the n over n plus 1 factorial. Okay? And if you do some nice cancellations, let's see here. Let's cancel some stuff. So like this n plus 1 factorial cancels everything except the n plus 2, yes? And this 7 to the n, that completely goes away. And what's left is a single factor of 7. And overall, you end up with n plus 1 times 7 over n, there's an n right here, n times n plus 2, which as n goes to infinity, what does this go to? It actually goes to 0, which is less than 1. So what's going on with this? Converges how? Absolutely by the ratio test. Okay? Questions on that? Well, lastly, some of you didn't realize that 0 was right in the middle of this interval, okay? So really, I mean, what you have to do is you kind of have to split this thing up into the integral from -2 to 0 plus the integral from 0 to 3. And if you just look at, for instance, the integral from 0 to 3, and let's just write this as x to the minus 3 dx, then you realize, and by the way, going, 0 at the lower endpoint, you would take the limit as a goes to 0 from the right or something, yes? But the antiderivative of this thing is like -1/2 x to the -2 evaluated between 0 and 3. And if you plug in 3, you get like -1/18. It's going to be minus negative, which is plus. Now, if I go to 0 from the right, I'm going to literally get infinity here, okay? So that just the integral from 0 to 3 diverges to plus infinity. And what did we say? The minute one part of the integral diverges, what do you say about the whole thing? Diverges, right? So this thing, right? So the whole integral diverges. Okay, this is the one where I didn't have a whole lot of mercy. Some of you were doing, like if, for instance, if you just straight up did the antiderivative and plugged in the endpoints, you weren't going to get much. But even some of you, like, for instance, if you took the limit and you ended up getting 0 as the limit when 0 was in the denominator, I wanted to make sure that that one hurt you, okay? I don't want you doing things like that. When you have 0 in the denominator, okay, and some constant in the numerator, you're going to not get 0, okay? You're going to get something massive, okay? So I just wanted to make sure that you really learned your lesson on that one for sure, okay? Question on that? Any questions? Well, that's that, okay? And here's where we're headed. We're actually done with chapter 10. So now we're in chapter 11, believe it or not. Okay, it's amazing. And that's where we start talking about vectors. How many of you are in physics right now? Okay, so you probably talk about vectors as some kind of physical quantity. We're going to do that as well, but we're also going to look at some of the theoretical underpinnings behind what a vector actually is. And the first place we're going to start is in the plane, and then we'll move into three-dimensional space. And that is going to represent a transition from calculus in the plane, which is what we've been doing for Calc 1 and Calc 2 and pre-calculus, et cetera. We're going to transition from calculus in the plane to calculus in three-dimensional space and even multi-dimensional space, okay? So we're about to transition there once we get a couple sections into chapter 11, okay? So let's do this. Vectors in the plane. This is the first section of chapter 11, okay? A quantity that can be described by a single real number is called a scalar, okay? And that real number could be negative as well. It doesn't have to be positive. And we'll talk about scaling things by certain quantities. And that means multiplying by some real number. If we wanted to represent quantities that required both a sense of size and direction, then we can do that with a directed line segment. A directed line segment. I'm being very precise with my language right now, okay? A directed line segment can both indicate direction and size or distance, okay? A directed line segment can do that. Not yet talking about a vector. You'll see what I mean by a vector in just a minute, but here's an example of a directed line segment. You get a sense of both direction, that is movement from P to Q along that line segment. So that's why you put the arrowhead at Q, because you're thinking of moving from P to Q. But you also get a sense of how much movement took place, yes? You get a sense of the direction of movement, and how much movement took place because of the length of that line segment, right? In physics, we would use terms like displacement. So some kind of object is being displaced from P, it was at P, and it's moved across some distance in the direction, and in that straight line direction, ending at Q. Forces can often be, notated in this way or thought of in this way as well, okay? But the word displacement is going to be a big deal for us, for sure. So two directed line segments are said to be equivalent if they have the same magnitude and direction, okay? So if we're chiefly interested in movement from some point to another point and how much movement and in what direction that movement happened, then even if, that movement happened starting from two different points and ending at two different points, as long as that movement was in the same direction along the same distance, we'll consider those to be equivalent. Okay, so the set of all directed line segments that are equivalent to a given line segment, directed line segment, is called a vector. Okay, so a vector, a specific vector is really like representing an infinite collection of directed line segments. Does that make sense? That vector can literally be drawn anywhere in the plane, okay? So when I say vector, I'm not just talking about one thing, I'm talking about an infinitude of things that are actually equivalent to each other, yeah? But I can also talk about any individual directed line segment that belongs to that class of equivalent vectors. And there's some interesting notation. I have a hard time drawing a bold-faced V with my hand, you could do that in typeset, but most of the time when I write a vector, I want to put V with like a little arrow over it, okay? Any questions so far? So this stuff's like just pretty standard stuff as far as vectors are concerned. Since we're interested in length and direction, we need to have a way of notating length. Okay, so the length of a directed line segment, PQ, is also called its magnitude. Okay, and it's denoted by, like the book uses these two double lines. Sometimes I'll slip into the habit of just using single absolute value lines, but that's talking about the length of this thing, okay? Which is essentially measuring how much movement has taken place along PQ. And we're also interested in direction. We'll get to that shortly. Okay, show that U, the directed line segment from -4 to 1,8, and V, the directed line segment from 2 - 1 to 7,7, are equivalent. Well, okay, let's do it. Okay, so -4, 1, 2, 3, 4, okay, to 1, 8, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So essentially what's happened here is, okay, so this is U right here. Okay, that's U. And V goes from 2 - 1 to where? 7, 7. 1, 2, 3, 4, 5, 6, 7, and then up 7. Okay. Boy, they look pretty similar, don't they? Well, the way that you can show that they're equivalent is you can basically count how much displacement has taken place in both the X and the Y directions. How much displacement has happened in the X direction for you? How many units of X displacement have occurred? 5. And how many units of Y displacement have occurred? 8. Well, what's going on with V? How many units of X displacement have occurred here? 5. And how many units of Y displacement? 8. And eventually what we'll do is we'll actually write this vector as 5, 8, and that's talking about x, how much x displacement is having. And we'll put these little angled brackets to kind of notate that this is indeed a vector quantity and not like just a point or something, okay? And v is 5, 8. So these things have the same amount of x and y displacement, okay? And eventually we'll also realize that we can easily figure out that 5 by simply taking the difference between the x coordinates, okay? You're saying in moving from -4, 0 to 1, 8, I have gained 5 units of displacement in the x direction. That's the same as 1 minus -4, yeah? So we'll kind of talk about that eventually as well. Okay, so those two things are the same because they have the same amount of x and y displacement. And as such, they're going to have the same magnitude and direction. So they're equivalent as vectors. Any questions on that? Let me get rid of this. A vector is said to be in standard position if its initial point is at the origin. Okay? If V is a vector in the plane in standard position with terminal point V1, V2, okay, so what I'm saying here is it's emanating from the origin. So this is V1, this is V2. Okay, so there's the terminal point right there. I draw this. Okay, I'm going to call this vector V, and then I write this as V1, V2, just like I was saying up there earlier. Okay? What that means is if I were to put this vector with its initial point at the origin, I would go V1 units in the x direction and V2 units in the y direction. Of course, this is directed direction, right? So like if V1 was negative, I would go to the left by V1 units. Okay. This is called the component form of a vector. Okay. So let me just say that two vectors are the same if and only if their x displacements and their y displacements are the same. So here I'm thinking of u as being u1, comma u2, and I'm thinking v as being v1, comma v2. Okay. They're going to be the same as vectors if and only if their x displacements and their y displacements are exactly the same. Okay? Any questions on this so far? Any questions? Well, let's move on then. Okay, if a directed line segment from P to Q is equal to V, and P is equal to P1, P2, and Q is equal to Q1, Q2, then the component form of V is, what do you think? How much x displacement has occurred in moving from P to Q? Only think about x displacement. How much x displacement has occurred in moving from P to Q? Q1 minus P1. Yeah, that's how much x displacement has occurred. Yes, that's how much difference there is in my movement in the x direction. What about in the y direction? Q2 minus P2. Okay, so the component form of V is going to be Q1 minus P1, comma, Q2 minus P2. And you put those angled brackets to remind ourselves that we're talking about vectors here. Yeah? Okay. The length of a vector is also called its magnitude, as we have already discussed, and is denoted the same way as a directed line segment. So you would put the double bars around it, or I don't care, you can use single bars, okay? Just absolute value symbols to represent the length of a vector. Okay, the length of the vector V equal to V1, V2. Now just think about this. Okay, so here's V1, here's V2. Okay, so here's my vector V. Okay, then, I mean, come on. What is the length of this hypotenuse? Well, I have a little right triangle right here. This is V1. This is V2. Do you see? Yeah? So the length of the hypotenuse is going to be the square root of the squares on the legs. Yes, that's just the Pythagorean theorem. So it's going to be the square root of V1 squared plus V2 squared. No problem. Okay, so that's where this little formula is coming from right here. Okay? Make sense? Just the Pythagorean theorem. Any questions on that? Any questions so far? I know that some of you have seen this stuff in a physics context before. If the length of V is 1, you call V a unit vector. Okay? If the length of V is 0, then V is the 0 vector. And there's an alternative notation for that. It's like bold-faced 0 or 0 with like a little arrow over it. Okay, it's the 0 vector. It's the vector that really has no direction or magnitude. It's just devoid of any direction or magnitude. Yeah? Okay, so that's interesting. Okay, hang on, let me erase this. Let's talk about multiplying a vector by a constant or a scalar, okay? So suppose I have a vector, v1, v2, and I multiply it by a scalar. Then for instance, if say that c was like 2, then basically what I'm doing is I am distorting the x and y displacement by that factor, that scalar factor. So like if I'm multiplying by 2, the x displacement, whatever it was before, is going to be doubled, yes? And the y displacement will be doubled, yeah? And so I kind of have drawn this picture to illustrate that, yeah? I mean, you can almost imagine that really this is like 2 copies of the vector v. Do you see what I'm saying? Kind of stacked end to end, right? There's v, and there's v again right there, yeah? But like multiplying by a scalar basically gives us a vector that's been stretched out by that constant factor. If that scalar happens to be negative, it will also do what to it? You guys know? It'll actually flip it around. So instead of x displacement going the one way, it'll go the other. And similarly for the y, okay? So that's what this picture is. If I multiply by a negative, it's going to flip the x and y displacements in the opposite direction, yes? And as such, you're going to have a vector that looks basically the same, but the initial and terminal points have switched around. Now the arrow is going the other way, okay? Any questions on that so far? Any questions? Let's talk about adding 2 vectors together. Adding 2 vectors, okay? So if I add 2 vectors, what I'm doing is I'm combining their displacements in both the x and the y directions. So if I add 2 vectors together, I'm saying, what's the combined x displacement? Well, you have to add the x coordinates together, yes? And similarly, you say, what is the y displacement? You would have to add the y coordinates together. And what's happening here is basically, I'm taking the vector u and the vector v, and I'm kind of stacking them end to end. And the u plus v vector is just going to be like the third side of that triangle, basically, because you've combined the x and y displacements of both u and v, okay? Let me ask you a question. Stare at that picture for a minute. So this is kind of a cool, like, do you guys realize that down here, that's another copy of v? And this right here, if I drew that, this right here is actually another copy of u. Do you see that? So this is like a little parallelogram that's like a helpful picture to have in hand. So here's one thing that I would ask you. Look, what about the magnitude of u plus v how does that compare to the magnitude of u plus the magnitude of v? Which of those two things is greater? Just staring at that picture for a minute, because I've put them in a triangle with one another. What do you think is going to be the longer distance? U's length plus v's length, or the length of u plus v? What do you guys think? U's length plus v's length is going to be longer. That's oftentimes called the triangle inequality because of this picture. Okay? U's length plus v's length is going to exceed that of u plus v because of this triangle picture, yes? The shortest distance between 2 points is a straight line. Yeah? In the plane, at least, that's true. Okay? And so walking along u and v, you're going to cover a larger distance than if you walk along the sum of those two vectors, the third side of that triangle. This is oftentimes referred to as the triangle inequality, or this, because of this picture that we just drew. Okay? And I'll repeat that here pretty soon, but I just wanted to point it out right now. Okay? What about the difference between two vectors? Well, you can almost think of this as like u plus negative v, right? And then you could basically add those two things together. But what's going on with a picture? Okay, well, if this is v right here, okay, here's v, then basically minus v is going to point in the opposite direction, yes? And if I want to do u plus negative v, that's going to be this vector right here. Okay? Okay, so here's u minus v. U minus v is this vector right here. It's the same as this one over here. Okay? This is also u minus v. Okay? So the way I like to look at this, I mean, I don't know if you can see the picture very well, but if this is u and this is v, oops, what did I just do? I just wrote u again. And that's v, okay? Then where is u minus v? It's right here, u minus v. And the way you can kind of see that is what happens if I took v and added it to u minus v? What's going to cancel? If I take v and add it to u minus v, what cancels? V does, and you just end up with u, yeah? Right, so it's what I always do, u minus v, you kind of put the arrowhead on u, and you put the terminal point, or you put the initial point on v's terminal point. And there you have u minus v. Here's a picture that I often like to draw that is helpful. If this is u, and this is v, okay, then, and let me redraw u again here, and this is v, okay, then of course, going along this diagonal, that's u plus v, is it not? Yeah? And where is u minus v? Well, it's right here. Okay, so this guy is u minus v. Okay? So actually you can draw a little parallelogram using just u and v, and the diagonals of that parallelogram are going to be u plus v and u minus v respectively, depending on, you know, which direction you put the arrowheads there, okay? Or which diagonal you're looking at. Does that make sense? Hopefully, okay. Okay, so there's some nice geometry going on here that we'll definitely take advantage of eventually. Any questions on this so far? We talked about scaling vectors. We've talked about adding vectors. We've talked about subtracting vectors. Yes. And what that represents. Just again, all of it is about combining x and y displacements, or stretching or shrinking or flipping around x and y displacements in the context of multiplying by a scalar. Okay. Okay, how would I compute this? Well, first of all, if I have 2 times the vector 5, 1, okay, what's that going to be? What's that? 2 times 5, 2 times 1, I get 10, 2, plus negative 7, 3, which is, now I just have to combine. I first stretched that first vector by a factor of 2, yes, in both the x and y directions. And then I added it to the other vector, and I'm asking what is the combined x and y displacement of these two vectors? And I will see that it's 3 in the x direction and what in the y direction? 5 in the y direction, yeah. Okay. So that's 3 comma minus 5. Any questions on that? Okay. Here are some properties of vector operations. Is it obvious to you that if I add u to v, then that's the same thing as adding v to u? Okay. After all, I'm just going to be adding their x and y coordinates, and I can flip those things around. The second property, that's called, so by the way, this property right here is called the commutative property. This is the commutative property. What is this called? Does anybody know? That's called the associative property. Exactly right. Associative property means, like if I had 3 vectors to add together, how do I know which ones to do first? The answer is, doesn't matter. Just make a choice, yeah? So the associative property is basically that second thing. Of course, if I add the 0 vector to u, I get u right back, okay? This is oftentimes referred to as the identity relation, okay? This right here is often referred to as the inverse relation. Basically, if you add u to its negative, then the x and y displacements are going to be blitzed. Does that make sense? Negative of u is going to have the opposite x displacement and the opposite y displacement. So if I add them together, I'm going to go nowhere. Does that make sense? I'm going to actually be, in effect, back where I started. Okay? C and D here are scalars. These are scalars. Okay? And there's a nice, you basically, what this is a distributive law. Okay? You can essentially distribute a vector over a sum of scalars. That's what this is saying, yes? But similarly, I can distribute a scalar over a sum of vectors. So these guys right here are often referred to as the distributive laws. Distributive laws, yeah? Okay. This right here is often referred to, it's sort of stupid. Of course, if I scale a vector by 1, I just get the vector right back. This is another identity relation. Kind of like u plus 0 is u, 1 times u is u, okay? And of course, if I scale a vector by 0, that just kills the x and y displacement, yeah? And I'm gonna end up with a 0 vector, okay? Any questions on those identities? They're not super complicated or controversial, yes? These are things that you would probably accept whole cloth, okay, without too much convincing. Nonetheless, let's look at property number 1, the so-called commutative law. Why is it true? Well, if u plus v, if we represent them by like u1, u2, and v1, v2, if I add those together, then I would need to add u1 to v1 and u2 to v2, and those will become my new x and y displacements, yes? But then, of course, those are just numbers, and I can flip those around, can't I? Yeah? That's the same thing as v1 plus u1, comma, v2 plus u2, and then I can break them up and just have v1, v2 plus u1, u2, which of course is just v plus u, yeah? So as you can see, you can kind of walk your way through these properties if you were so inclined. I just wanted to show you that, okay? That's how you would verify property number 1. Magnitude. So what happens if I take a scalar? Okay, so this c right here is a scalar. and I multiply it by a vector. What is the new magnitude? Well, it's going to be that scalar times the magnitude, but you have to be careful because the scalar could be negative. Does that make sense? So it's actually the absolute value of that scalar times the old magnitude of that vector. So like if I multiply a vector by 2, then its new magnitude will be double what it was before. Yes? If I multiply a vector by a half, then its new magnitude will be half of what it was before. Okay? If I multiply a vector by negative a half, its new magnitude will be half of what it was before. Yes? So this is probably an uncontroversial thing as well. Let's actually go through why this is true. Look, the length of CV is equal to the length of CV1, CV2. Okay, I've just multiplied X and Y displacements by C. I would have to use the Pythagorean identity. So that's going to be the square root of CV1 squared plus CV2 squared. Yeah. What do you think? What can I factor out of that? What can I factor out of that sum underneath the square root? C squared. Yeah. Factor out C squared. And here's where I find out if you've been paying attention to a word I've been saying about taking square roots of squares. The square root of C squared is not just C, right? It's the absolute value of C, yes? Okay, so it's going to be the absolute value of C times that Pythagorean square root, which that thing is just the length of V. Okay, so there's a little verification that indeed multiplying a vector by a constant simply multiplies the magnitude by that same constant in absolute value. Okay? Any questions on that? Probably not very controversial either. And this is the thing I talked about before, yes? The so-called triangle inequality. I already gave the explanation, but let me redraw the picture. So if this is U, and then I draw V emanating from the terminal point of view, okay, so here's V, then U plus V is this guy. Okay, U plus V is that vector right there. And of course, the distance along the U plus V side of that triangle is shorter than the sum of the lengths going along U and V, yes? So as I said, this is referred to as the triangle. Well, this is one of the most important inequalities in all of mathematics, the triangle inequality. Okay, triangle inequality. Very, very important inequality. Okay. Let's talk briefly about finding unit vectors. To find a unit vector in the same direction of a given vector, what do you think you should do? Suppose I had a vector that was of length 5, and I say I want a vector that's not length 5, but length 1, but is pointing in the same direction. I would divide by 5 or multiply by a fifth, yes? What if I had a vector that was of length 70? Divide by 70 or multiply by 1/70. Yes? Therefore, in general, I should multiply by 1 over the length of the vector. And that will give me a unit vector in the same direction. Okay? Multiplying by a scalar changes only the length, not the direction. Unless the scalar is negative, in which case it flips it around. Yeah? A unit vector in the direction of V is U equal to V divided by the length of V. But that's the same thing, by the way, as multiplying by 1 over the length of V, whatever that is. Multiplying the vector V by 1 over the length of V. Yeah? Okay, any questions on that? So if I want a unit vector in the same direction of a given vector, I have to multiply by 1 over the length of that vector. And that will give me a unit vector in that direction. Okay. There's a couple of special vectors that physicists are obsessed with. In fact, they're also obsessed with one in the third dimension called K, okay? Which are the vectors 1, 0, which is basically displacement by one unit in the x direction only and no displacement in the y direction, yes? Similarly, J is the vector that is displacement by one unit in the y direction and no displacement in the x direction, yeah? But what's interesting about these is you can actually write a given vector using I and j, okay? So what you do is you say if v is equal to v1, v2, then of course that's the same thing as v1, 0 plus 0, v1, yeah? And you say, hey, that's the same thing as multiplying I by v1 and j by v2, those scalars, yeah? So another way of writing a vector is by simply taking a scalar times I and a scalar times j. And basically the scalars are your x and y displacements respectively, okay? So for instance, if v was like the vector 3, comma, -2, another way to write that would be what? In terms of I and j. 3, I plus -2j, and sometimes you write that as -2j, okay? Incidentally, you'll notice that I oftentimes write I like this, and I'll write j like this, okay? Just so that you realize what I'm talking about, okay? Does that make sense? Hopefully? It's pretty common notation in physics. We call this a linear combination of I and j. V1 is called the horizontal component of V. I oftentimes call it the X displacement or the horizontal displacement. And V2 is called the vertical component of V, or the Y displacement, or the Y component, or the vertical displacement, okay? Those are all kind of interchangeable terms. Questions? Anything at all? You guys are quiet today. Let's see. I want to see if okay, hang on. You know what? I'm gonna stop right here because I have a couple more things to talk about, but I'm gonna stop right here. We'll talk about direction next. Direction will be the next thing that we talk about. Okay.